We've said this before, but it can't really be repeated enough. Change is an essential part of software development, and design has to take this into account. The number one reason that software changes is due to feature enhancements. If the software can be designed with a reasonable idea of how it might change over time, then it may be able to accommodate change without deteriorating too much over time. As an example, in our SimuDuck application, we know that we're likely to add different kind of ducks in the future, but we also know that we're likely to add different kind of duck behaviors. We'd like to design a system that is robust to both kinds of enhancement. This leads us to our first design principle. Identify the aspects of your application that vary and separate them from what stays the same. Let's look at this principle as it applies to behaviors in our SimuDuck application. We want to separate and encapsulate the parts of our application that vary from the parts that stay the same. The flying behavior in our application is something that varies. Using inheritance for flying behavior, as we did in our original design, means that all subclasses get the same behavior. If the default behavior does not make sense for a particular duck, the subclass has to override that behavior. Since flying behavior and quacking behavior vary, our new design is going to take them out of our abstract duck class. The abstract duck class will still be the superclass of all ducks, but the flying and quacking behaviors will be taken out and put into their own class structure. Each separate flying behavior will have its own class, and each quacking behavior will also have its own class. The different classes will contain different implementations of flying and quacking. Each flying class will contain the implementation of a single method, fly, and each quacking class will contain the implementation of a single method, quack. Since all of our flying classes will implement the method fly, they effectively implement the same interface, an interface with the single method signature fly. Something similar can be said about the quacking classes. In fact, these interfaces, let's call them fly behavior and quack behavior, will be a key part of our design. Which brings us to our second design principle, program to an interface, not to an implementation. What does this mean? When a client programs to an interface rather than a concrete class, it gives the client the ability to choose from multiple different implementations of that interface. In the case of our SimuDuck program, we will represent individual fly behaviors as an interface named fly behavior with a single method fly. We can implement that interface in several different ways. For example, fly no way will make the duck not fly at all. Fly with wings may make the duck fly like a normal duck. And fly like a rocket may make the duck take off like a rocket. If individual duck objects program to interfaces instead of individual implementations, then they're going to have the ability to use any of the implementations that implement that interface. A couple more notes on interfaces. Interfaces change less than implementations. That's because interfaces are actually subsets of implementations. They're just the method signatures, whereas the implementations are the signatures plus the bodies. Ideally, when you program to an interface rather than an implementation, the implementations can be created, modified, and swapped out without affecting the rest of the code. Here's an example of a problem that comes up when you don't use an interface. In the diagram on the left, we have a concrete class that depends on another concrete class. If you modify the class on the bottom of the diagram, you run the risk of breaking the system because the class on the top of the diagram may have directly depended on the portion of code that you changed. In the diagram on the right, you have a concrete class that depends on an interface and another concrete class that implements that interface. If you modify the concrete class on the bottom, the one that implements the interface, your system will still work because the new implementation must still conform to that interface. The concrete class that depends on the interface still works because the interface has not changed. So let's look at how we're going to implement our design. We have a fly behavior interface with a single method, fly. And we have two different implementations for it, fly with wings and fly no way. We have something similar for the quacking behavior. We have a quack behavior interface and three different implementations, quack, squeak, and mute quack. By the way, notice that we are not doing the same thing for the swim behavior. We're assuming that the swim behavior is going to be implemented the same for all ducks. So we're keeping swim as a method in the abstract duck class. Here are some of the benefits of this design. First, ducks are not the only objects that can use behaviors. These behaviors are not bound in any way to the duck class. Second, since we're programming to an interface, it's easy to add new behaviors without modifying existing code. And finally, the behaviors have the benefit of being reusable without incurring the problems associated with inheritance. This all sounds wonderful, but we haven't actually talked about how we connect these behaviors to the duck objects yet. Well, here's how we're going to do that. In our abstract duck class, we'll have two fields, one that holds a fly behavior object and one that holds a quack behavior object. And remember, fly behavior and quack behavior are interfaces. We haven't committed to any particular implementation here yet. In addition to these fields, we have two methods, perform quack and perform fly. The perform quack code simply uses the quack behavior object to call the quack method. In other words, it just calls quack behavior.quack. And the perform fly method does something similar. In the constructor of the concrete classes, the quack behavior and fly behavior variables are actually assigned specific concrete implementations. Here, the mallard duck class is instantiated with the quack implementation of quack behavior and the fly with wings implementation of fly behavior. A great benefit of this design is that the fly and quack behaviors are encapsulated in objects that are assigned to instance variables. If at some point during the program it was appropriate, these variables could be reassigned a different behavior. Here's an example of a new duck being created and the various behaviors being activated on it. Notice perform quack and perform fly. And finally, this is an overview of the new design. We still have an abstract duck class and duck subclasses that inherit the method swim. But now we have a way of providing different fly and quack behaviors to any duck object, and even swapping them out at runtime. A couple of things to notice here. First, consider the original design that consisted of only the abstract duck class and its subclasses. Is there any benefit to that design over this one? You don't need to pause the video for this question, but just give it a few seconds of thought. From my perspective, the main benefit of the original design was its simplicity. It's true that this new design gives you the flexibility of changing certain behaviors at runtime, but there's also more coupling here, and more classes to keep track of, and more levels of indirection involved in performing a behavior. Remember that patterns are just tools in your toolbox. Always weigh the pros and cons of using any design pattern. One thing that we haven't really discussed in regard to this particular pattern is the move from an inheritance structure to a composition structure. This is one of the things that interests me the most about this pattern. You're taking something that is most naturally an action, like flying or quacking, and instead of making it a method, you make it into an object. It seems to run against my intuition of what should be considered data and what should be considered an operation. But the benefits of this design are clear. This brings us to our third design principle: favor composition over inheritance. Composition is a has-a relationship, while inheritance is a is-a relationship. Defining the flying behavior as an object allows us to create a family of different flying algorithms that implement an interface, and it allows us to swap out different flying behaviors at runtime. In the new design, a duck object has a fly behavior object, which in turn contains a fly method. In the original design, a mallard duck object is a kind of duck and inherits the fly method from its superclass. Regardless of whether it were to use the inherited fly method from the abstract duck class or override it with a fly method that did something else, the decision would have to be made before the code was compiled. Once the fly method was compiled for the mallard duck, it could not change. In the new design, the behavior can be changed at runtime simply by assigning a new fly behavior object to a duck's fly behavior variable. Another benefit of composition over inheritance is the fact that reasoning about a particular fly method is simplified, because you only have to worry about the method as it conforms to its interface. You don't have to worry about what subclasses might have to override the fly method, like you do in the original design. And now that we know the details of this pattern, we should also know its name. It's called the strategy pattern. The strategy pattern defines a family of algorithms or behaviors, encapsulates each one, and makes them interchangeable. Strategy lets the algorithm or behavior vary independently from clients that use it. So we've looked at our first pattern, and it's a great one to know. In the next video, we'll look at the observer pattern. We'll find out what it is, why it's useful, and we'll look at a few places where the Java library uses this pattern. I'll see you there.